The example we're going to use for confidence intervals is throwing tacks, which is something that you guys did during the probability unit. It's a little dark, but hopefully you can see. Here's some tacks being thrown, and we're keeping track of when it lands on side and when it lands point up. Now, the important thing about this is, what about the population? All right. Unfortunately, we don't have a theoretical model for this experiment. Which means all we have is experimental. So let's go and see the results. As it said before, all right, so we ran it a bunch of times. 27 times was on side, 11 times was point up. So we have no theoretical model to calculate probability. We only have experimental. So well, let's calculate it. We have total number of tosses, the number of times it landed point up, and we have a probability of 28.9% chance. Now, the real question is this the true value for this probability? The answer is no, it isn't. Right? Because this is just one sample. If we take another one, we'll probably get something a little bit different. That's an indication that this is not the true probability. Next question, is there a way to calculate the true probability for this probability? And the answer again is no, unfortunately not. But there is a way to calculate a range that we're pretty sure the true value is within. This range is called the confidence interval. So to get the confidence interval, we of course start with our sampling distribution. Everything around this unit is about sampling distribution. Sampling distribution is going to be actually about sample proportions. If we think about probability, our 28.9% chance, it's actually a proportion, right, not a mean. And the sampling distribution will be centered on the true population proportion, which we don't know. So what we're going to be doing is estimating this true population proportion with our sample proportion. And that's going to become an estimated sampling distribution, centered around our 0.289. Now we have to go through the shape. We of course started with center, shape, of course what's going to come next is spread. We have to see what shape it's going to be. If you remember, that comes from this summary page. All right, we're talking about proportions. Is it two sample or one sample? All right, well, we just have one sample. So we're going kind of this way. Of course, we don't have t-distribution, so it's either going to be normal or nothing. And so here's our criteria that we have to check, which we can start doing now. It's a simple random sample. That was the first one. We can check sample size times p, sample size times q, which is 1 minus p. They're both bigger than 10. That checks out. And the population is actually bigger than 10 times the sample size. So the shape has been verified as a normal distribution. Spread comes from this equation for standard deviation, which again, coming from a summary page, I can show you quickly. Sample proportions, yes, it's normal. There's our equation, right, that we used. So we go that way. So if that's our standard deviation, we can now figure out the rest of the distribution. Going out 3 standard deviations, those are our numbers. Let's remind ourselves that this distribution represents all possible sample proportions, p hat, but this is assuming that the true, or the center of the distribution is 0.289, which we're actually pretty sure is not the case, but that's why we're using an estimated distribution. And we can say a few things that we learned a while ago, such as 68% of all p-hats, or sample proportions, will be between or plus or minus 1 standard deviation, 95% between 2 standard deviations, and 99.7% between 3 standard deviations. To talk about the concept of sample proportions, or sorry, confidence interval concept, we're going to focus on just the 68% interval for the time being. We're going to actually represent the 68% interval a little bit differently. Instead of shading the area, we're going to make it a line that goes from 1 standard deviation below to 1 standard deviation above. That's the length centered on our sample proportion. Now, this we're going to actually call sample 1. You can anticipate there are going to be more samples that we're going to talk about. And somewhere out there in some ideal universe, there is a true sampling distribution of sample proportions. All right, centered on the true value of our probability. Now, if we were trying to map this interval onto this true distribution, it might look something like this. Not entirely sure because, of course, we don't know the value of this p. But what we do know is it's likely the center of our sample is probably going to be a little bit different. So it might look something like that. If we take another sample, it might look like that. Third sample, something to pay attention to. All of these intervals contain our actual true population proportion. That may not always be the case. We might get a sample like sample 4 that doesn't contain the true population proportion. Now the question is, what percentage of these samples will contain this true population proportion? Well, it turns out 68%. It's very convenient. 68% of all possible sample intervals will contain the true population proportion. This is now our confidence interval. We can talk about it in our standard notation and vocabulary, which will look something like this, in which our true population proportion is between 0.215 and 0.363. And we can say that with 68% confidence, which is to say 68% of all samples will contain that true proportion. Of course, 68% isn't very much. That means 32% don't contain the true population proportion. So that's not very confident, really. So what we might want is a question about a 98% confidence interval. That would be much more confident, which means we're going to have an interval that's probably going to be something like this, because it needs to contain 98% of all possible sample proportions. We need the lower and upper bound, which will be the bounds of our confidence interval. In order to get the lower bound, I'm going to use this inverse norm function from the TID4, the syntax of which is area, mean, standard deviation. The area it refers to is not the purple area, but the area to the left of the boundary. So we're going to have to quickly find that area. Of course, the purple is 98, so we can split that in half, which means each side is 49%, which means this whole half of the curve is 50%. We can subtract the 49, and the area that we're interested in, the red area, is 0.01. Now we can get our lower bound, which is 0.117. Here's our lower bound. Once we have our lower bound, this is symmetric. So this distance from the center to the lower bound is the same as center to the upper bound. So we can do a quick calculation like this. This is that difference that we're now adding to the center. And we have our upper bound. And now we can say what the confidence interval is. So we have from 0.117 to 0.461, the true population proportion, right, the actual probability of attack landing point up, is somewhere between these two values, and we can know that with 98% confidence, which is to say 98% of the time of the samples will fall in that range. Now, that's confidence intervals, right? So just finding the lower bound and upper bound, it's actually not too cumbersome, and you got it. There is one more issue that we do need to talk about, and that's the width of this interval. So if we were to get the width of this 98% confidence interval, it's just a simple subtraction, right? We get 0.344. If we think back to the 68% confidence interval we got before, it would have a width of 0.148. As you would expect, the width of the 98% confidence interval is much bigger than the 68%. In fact, 2.3 times bigger, which could be thought of as 230% bigger, which is a little unfortunate. Unfortunately, with higher confidence comes a bigger range, which means there are more values that are possible. That's inconvenient in many instances. So there's a question about, can we actually maintain a high confidence and reduce the width? And in fact, there is a way of doing that. In order to reduce the width of the confidence interval without reducing the level of confidence, it's the sample size, n, which has to be increased. Now, I'm not going to do that during this video because I'm going to let you guys work with that in class. Before we end, though, I want to do one more thing, which is to show you how to do some of this on the TI-84 calculator. Now what we'll do is we'll go back a little bit to this 68% confidence interval, and let's look at how we are going to do this in the calculator. You'll find the function that we're going to be using in stat and calc and then tests. So we're in these tests. And if we go down, these are all our Z and T tests. All right, you can see where we have intervals. All right, Z interval, T interval. Now, this is a one proportion Z interval. So this is the one that we want because we're using the normal distribution, confidence interval, proportions, one proportion. So we get this. Now, what the calculator is going to be looking for are counts. Right? So how many successes? All right, well, how many times did the attacks land point up? That was 11 times. N is the total number of tosses, which is 38. We have confidence interval, which in this case is 68 or 0.68. And we ask it to calculate. And you can see it gives us 0.1 or 0.216. And you can see this is 0.215. All right. The difference is, right, we have the sample proportion that the calculator calculates, which is 0.289473, blah, blah, blah. Right. You can see that the proportion that we used was truncated, or rounded rather, 0.289. So there's a little round-off error. and that accounts for that difference. And the other level, or the upper bound rather, is 0.363, which if we look over here is 0.363. So it's pretty actually straightforward. You just have to know, which function to use. It gives you actually the sample proportion, and those are the two upper and lower limits for our confidence interval.